Hello students, in this video we'll discuss the Fast Fourier Transform. Let's recall that if we're given a vector z in L2, we can define z hat k to be the sum. J goes from 0 to n minus 1 of numbers zj, and then zeta to the negative jk, like that. And of course, we could write this as a matrix equation too. So here, zeta is just the primitive root of unity, 2 pi I over n. And this allows me to write this in a matrix form. So our discrete Fourier transform equation is that z hat is equal to f matrix fn. And we know what the inverse of this matrix is too from a previous video, fn of z. And so this is an n by n matrix. So this is going to require n squared calculations, Okay. Now what we're going to do is we're going to actually make an assumption on n if n is even. So if n is equal to 2m, then define the even and odd parts. Then define z even of k to be z of 2k, right? Where k goes between 0 and m minus 1. And z odd of k is z 2k plus 1, where k goes between 0 and m minus 1. So there's m terms in each of these camps over here. And of course, what we can do now is I can compute z e hat, and then z 0 hat, right? So those things, so I had z e or z 0 hat, that would be fm z e or 0. And over there, there's m squared. Of course, m squared in this case is going to be what? Is going to be n squared over 4 calculations. For a total, if you do both of them, you get n squared over 2 calculations, okay? So the idea is that if we can try to use these z evens and z odds to compute the Fourier coefficients of f, then I'll be able to I can cut my computation speed in half, right? So, and the hope is that for every, if this is a general even power, I can do this for as many powers of 2 as I have in my number n over here, okay? So of course, what we want to do now is we want to actually parameterize these zetas based on n and m, right? So therefore, zeta m would be what? Would be e to the 2 pi I over m. And so the key feature of this is that if I look at, what we can say over here is that if I put a 4 on top over here, so in other words, if there was a 4 over there, that would turn into an m, right? So we're going to use that relationship. We're going to use that fact over here, that there's the relationship between zeta m and zeta n, okay? So let's do it now. So it's the first thing we're going to consider. Let's first consider the range of m. M goes 0, 1, 2, up to m minus 1, right? And if m is in this range, what can I say about z hat of m? Z hat of m is the sum. K goes from 0 up to what? Up to n minus 1. And then what? Then just zk. And then zeta sub n to the negative km. Negative km. Okay, great. Now I'm going to break up this k into even and odd terms, right? So if we break k into even and odd terms, what will we get? This will be equal to what? This will be equal to the sum. K goes from 0 to m minus 1. Now z on the even terms is equal to z sub even, so this will be z sub even of k. But those occur at the even terms, so that's going to be a zeta n, and that's going to be a negative 2k m like that, because I'm on the even terms. And I can look at the odd terms too, plus the sum. K goes from 0 to m minus 1 of what? Of z odd k. And then e, well, let's not do e, let's do zetas, right? So let's do zeta. So the zeta, I can't write the zeta right now. My zetas are poor. So let's write zeta. Zeta what? To the negative 2k plus 1 m. That's an n, of course. And now what I'm going to do is I'm going to use this relationship. We know that zeta n 2 with a squared. So what will zeta n squared be? So zeta n squared from this relationship, so zeta n squared is the same as e to the what? E to the 2 pi I, e to the 2 pi I over n over 2 by looking at fractions. And that's exactly equal to what? That's exactly equal to m. So this is going to be zeta m. Excellent. And so I can replace, what I can do is if I can take this zeta n to negative m out, then I'll have exactly what I want, right? So this would be equal to the sum, k goes from 0 up to m minus 1, then I'll have a z e k, then zeta m to the power negative k m, little m. Then plus this what? Plus this zeta n to the negative what? To the negative m. And then what? Then the sum, k goes from 0 up to m minus 1, zeta odd k, and then zeta m to the what? To the 2 to the negative km, like that. Excellent. And now I know exactly what that is. So that tells me what Zn is. This is Ze hat of m, and this is Z0 hat of m, and then with times that factor over there. So we've just proven that result. That's beautiful. So we have this now. So for this range of m, what can we conclude? We can conclude that Z hat of m for this particular range of m is equal to what? Is equal to Z even hat of m plus zeta to the negative m, zeta n to the negative m, which is just a complex number, then Z odd hat of m. So I've taken everything into which regime? I've taken everything into this regime up to addition and multiplication, which are only linear calculations in n. So that's a net gain for me, okay? For large n anyway. Now what happens if m is in the different regime? So if m is in this regime now, so if m is equal to m or m plus 1 or m plus 2 all the way down to n minus 1, then we can write m as big M plus L, where now L is between 0 and m minus 1, okay? And that's the whole kicker. So now I use the periodicity to put me in the right regime. So what's Z hat of n in this case? So Z hat of m in this case is going to be what? It's going to be the sum. It's the same expression over here. Do it like this. But now what are we going to replace over here? We're going to replace this, wherever I have an m, I'm going to replace with L plus m. L plus m. So we'll have the sum. K goes from 0 to m minus 1. We'll have ze hat e of k, and then zeta m to now what? To now the k times L, right? So k times L times L. Great. Because again, I'm just shifting everything by L. And then, since I know that if I shift the 2k plus 1, I have an m. I'm going to have an m over n. And we know that e to the 2 pi I m over n, by shifting by that factor of m, is going to give me a what? It's going to give me a m over n, which is 1/2. So I get a negative sign this time. So this is going to turn into an e to the 2 pi I times 1/2, which is just negative 1, right? So it's going to be a negative zeta n L times the sum, k goes from 0 up to m minus 1 of z odd of k, and then zeta m to the negative kl, And so in this case, what we get is this is going to be z even hat of L, and then minus zeta n of L, and then z odd hat of L. Again, I'm just shifting using the periodicity in this case. And then what can I say about that? This can be written, of course, as z e hat. What's L equal to? L is equal to m minus m capital. So this is going to be m minus m capital. And then minus zeta. And this, of course, is a negative over there. That's a negative zeta. That's, yeah, negative sign, negative. And then I'm going to have a what? A zeta to the negative m minus m capital. And then z odd hat of m minus m capital. And again, I've reduced the calculation of the discrete Fourier coefficients of z to those of the discrete Fourier coefficients of z even and z odd, and those are on level m. So I have a smaller dimension, I have a matrix of half the size of the overall matrix. And so that's beautiful now, because now this allows me to compute things up to additions and multiplications, which are linear. I get a net gain. So in other words, what we go from in this case is we go from a number of calculations of order 2. So the number of calculations goes on order 2, m, to just 2 number of calculations of order m, plus a small term, plus a smaller term, right? And so we get a net gain of calculations. And so this shows if I do this over and over and over again, we get a cumulative result by using this methodology. They sometimes call it a butterfly, because you're basically either choosing plus or minus on a trajectory. So the discrete Fourier transform says you can go from n squared to something on order of n log n, and that gives you a tremendous gain, especially for very, very high powers of n. So this is a very powerful calculational method. So of course, we haven't done this in general. We've only done it for n equals 2m. But if you see this, if n was equal to 4m, you could do this again. If it's equal to 8m, you could do this again. 16, you could do it again. 32, you could do it again. So the higher power of 2 you have, the more times you can do this scheme. And the more times you can do the scheme, the more times you can cut your calculations in half at every scale. And that proves the logarithmic, the extra log factor in your term. Thank you very much.